In the name of Allah, the most gracious and the most merciful of God. Assalamualaikum warahmatullahi wabarakatuh. Okay, here I am. Let me introduce myself. My name is Fathira Glenvenny Wahyudi, number of student 25/57148/PPA/07182. I'm a student of master's program in chemistry in Gajah Mada University. In this occasion, I want to review an article under the title Direct Printing of an Electrochemical Device and its Interface with Paper for Uric Acid Detection in Human Sweat. Okay, here's the outline of the presentation. First, research overview. Secondly, principle and methods. Third, materials and technologies used in biosensors. Fourth, biomarker. Fifth, main result. There's a figure and table. Sixth, critical analysis. Seventh, clinical application potential. And the last one is conclusion. Here is the research overview. First is clinical importance. Abnormal levels of uric acid or UA in body fluids can indicate or contribute to several serious health conditions, such as gout, Lesch syndrome, leukemia, and pneumonia. Therefore, monitoring UA levels is clinically important for early diagnosis and management of these diseases. Secondly, current limitation. Current clinical methods for uric acid or UA detection rely on uricase peroxidase enzyme systems, which, although sensitive and selective, are unstable under varying environmental conditions, such as pH, light, temperature, and air exposure. This instability leads to poor repeatability and reliability of measurements. Therefore, there is an urgent need to develop a more stable, reliable, and enzyme-free method for UA detection to ensure accurate and consistent clinical diagnostics. The third one is research aim. The purpose of this research was to evaluate the performance and efficiency of an LSG-based electrochemical sensor integrated with ONP-modified filter paper for uric acid detection in sweat, aiming to create an enzyme-free, mediator-free, and low sample volume system capable of detecting both normal and pathological UA levels. Okay. Next, the principle and methods. The principle of UA detection using LSG-ONP sensor. The biosensor operates by measuring the oxidation current produced when uric acid or UA in sweat is oxidized on a laser scribe graphene or LSG electrode enhanced with gold nanoparticles or ONPS. A small piece of Wetman paper holds the sample and electrolyte in a tiny volume of just 20 microliter. During the reaction, UA is converted to allantoin, releasing electrons that generate a measurable current through differential pulse voltammetry or DPV. The strength of this current directly reflects the concentration of uric acid, allowing for precise and efficient detection. Here's the methods which are simplicity. First is sweat sample, 20 microliter, so absorbed by Wetman filter paper, and an interaction with LSG electrode, so catalyzed by ONPS, and then the electrochemical reaction of uric acid and the electrons move to the electrode and generate an electric current. The flow or the current is measured with differential pulse voltammetry or DPV. The current signal proportional to uric acid concentration. Results compared with calibration data and measured or UA level UA concentrations or values. Okay, move to the next slide. Materials and technologies used in biosensors. Main electrode. The material is laser scribe graphene or LSG. The function is conductive surface for uric acid oxidation and reaction. The reason is not required in expensive high conductivity large surface area. The substrate we use polyimide sheet. Flexible media for LSG electrode fabrications. We use it because of heat stable, flexible, and easy to laser. Catalytic modification, they use gold nanoparticles or AUNPS, enhancing electrophotocatalytic activity and electron transfers. Because this high conductivity biocompatible increases oxidation current. The electrolyte or sample interface use Wattman filter paper number 1 or WFP1. The function is for absorbs and stores electrolytes and sweat. The reason is for high absorbency and large pores about 11 micrometer, stable and base signal. Electrolyte and redox probe. They use PBS pH 7.4 and calcium ferrocyanide and calcium ferrocyanide. Medium for voltammetry and signal stability testing. The reason is because of physiological conditions, reversible redox for calibration. The test interference selectivity. They use ascorbic acid or IA and dopamine or DA. Sensor selectivity tester for other biomolecules. The reason is for evaluating specificity towards UA. Primary detection method. They use differential pulse voltammetry or DPV. The function is for measuring oxidation current UA to allantoin. They use this because of high sensitivity and fast response, about 60 seconds. Analytical validation use UHPLC, ESIMS, MS. Comparison of actual UA levels in sweat. Is this because of accurate and highly precise, above 10% error. Material characterization, they use VESEM or field emission scanning electron microscope, micro, microscope, Raman, and XRD. They use this because of determine the morphology and structure LSG to confirm the formation of graphene 3D. Next, the biomarker. Biomarkers analyze is uric acid or UA, the end product of pure metabolism found in body fluids such as urine and sweat. Clinical relevance, abnormal UA levels are associated with gout, Lesch syndrome, leukemia, and pneumonia. Therefore, monitoring UA levels is important for the diagnosis and control of metabolic diseases, and detection through sweat allows for a non-invasive way to monitor these conditions. In healthy humans, UL levels in sweat range from 20 until 25 micromolar, while higher levels is above 25 micromolar up to approximately 750 micromolar indicate possible hyperuricemia or purine metabolism disorders. In this study, they developed base sensor was able to sensitively detect UA in the range of 10 until 750 micromolar, with a detection limit of 1.4 micromolar, covering both normal and pathological levels. The main result. A non-enzymatic electrochemical biosensor based on laser-scribed graphene or LSG modified with gold nanoparticles or AUNPS and Wattman filter paper has been developed. The sensor is capable of non-invasively detecting uric acid in human sweat. Working principle, oxidation of UA generates a current proportional to the concentration of UA, which is measured by DPV. Sensor performance. Detection range is about 10 until 750 micromolar, limit detection 1.4, which is the low, sensitivity 0.214, and response time about 60 seconds, stable for up to 18 days. High selectivity towards UA compared to interference such as ascorbic acid or dopamine. Result validated according to the UHPLC ESIMS method accuracy 98 until 104%. The conclusion, an inexpensive, fast, Fast, sensitive, and non-invasive base sensor with potential for real-time clinical monitoring of uric acid levels through sweat. Okay, we talk about the feature. We start from figure 1. This is about LSG base sensor fabrication schematic. A polyimide sheet is placed on a glass slide as a support. And then the PI surface is irradiated with a laser with an electrode pattern using an XY stage system according to the design. The irradiation process produces conductive electrodes from laser scarp graphene or LSG consisting of working, counter, and reference electrodes. Paper, paper interface is placed on top of the electrode area to hold the liquid sample. The electrochemical signal is recorded via computer, producing a current potential relationship curve. And the working mechanism analytes analytes or uric acid in sweat undergo oxidation reactions on the LSG electrode surface, resulting in electron transfer that is read as current. This current is directly proportional to the analyte concentration, enabling real-time quantitative detection. The significance: simple and non-invasive fabrication. Laser techniques directly form graphene without additional chemicals. Portable and flexible design. The polyimide paper combination enables use for monitoring biomarkers such as uric acid in sweat. Key advantages: real-time detection, noble sampling, and high sensitivity thanks to graphene's conductivity. And this is the conclusion of Feature 1, LSG based sensor fabrication schematic. My steps: PI sheet or polyimide sheet is attached to a glass slide irradiated with a laser to form electrode patterns. This working. So CA and reference paper is added as a sample medium, and then electrochemical signals are recorded. Working principle: uric acid is oxidized on the LSG surface, so the electron transfer occurs. The current generated is proportional to the uric acid concentration. The significance: this base sensor is non-invasive, real-time, and portable, with high conductivity from graphene that increases sensitivity. Let me move to feature 2. This is about the characterization of LSG electrodes. Figure 2A is optical photograph of the fabricated LSG electrode measuring 2.5 times 1.5 centimeter. The view-SAM image showing the laser engraving pattern on the polymer surface with an active area diameter 3.9 mm. The three-dimensional porous graphene structure is clearly visible, showing an open morphology that increases the surface area. So, the D cross-sectional image showing the thickness of the LSG layer at around 54 micrometer formed on the polyimide surface after laser irradiation. The structural analysis, this is show us in figure 2E and 2F. The 2E is the Raman spectrum displays peak at B, G, and 2D, indicating the formation of a graphitic structure with defects and sp2 domains characteristic of graphene. And then figure 2F, this is the XRD pattern, shows peaks at C, 002 and C 100 or 100, confirming the presence of structured graphitic layers. Significance: the laser scribing process successfully converts polyimide into conductive porous graphene. The 3D porous graphene structure increases the active surface area for electrochemical reactions. Characterization results in Raman and XRD confirm that LSG possesses graphene-like properties, making it ideal for sensitive and stable biosensor applications. This is the summary of figure 2 or characterization of LSG. The morphology LSG produced by laser engraving on polyimide forms a 3D porous graphene structure with a thickness of 54 micrometer and an active area of 3.9 millimeter. Structural analysis used Raman and XRD. In Raman, we got D, G, and 2D peaks indicate graphene with sp2 domains, and XRD about C002 and C100 peaks indicate gravitic crystallinity. Significance: the conductive 3D pore structure increases the surface area and sensitivity of the biosensor. I will move to figure 3 about the LSG sensor optimization. The image shows us this is an optical photograph shows the LSG electrodes VE, CE, and RE that have been fed with paper as an interface medium or paper interface to hold the electrolyte solution sample. And in the B, this is about cyclic voltammetry graph comparing three types of membranes. This is nitrocellulose membrane, nylon, and Wattman. The CV curve shows a characteristic of characteristic redox shape, indicating good conductivity. Wattman filter paper produced the highest current, selected as the best medium because it supports optimal ion diffusion. This one and this one. And then with graph C, the PBS solution or electrolyte volume optimization graph shows that the current increases up to a volume of 20 microliter, then stabilize up to 20 microliter, then stabilize, indicating the optimal volume for measurement. And with graph D, we got the bar graph shows the reproducibility between devices, device 1 until 5, with small current variations, indicating high sensor consistency and stability. And the meaning of the figure 3 is the selection of Wattman paper 20 microliter provides the best performance for the LSG paper system. The sensor shows high conductivity and reproducibility, indicating its potential for stable real-time biomarker monitoring applications. Okay, we move to the next slide. This is figure 4 about scan rate study. We go from 4A, cyclic voltammetry or CV graph of PLSG paper-based LSG at various scan rates 30, 50, 70, and 100. Oxidation and reduction currents increases with increasing scan rate. Indicating a reversible electrochemical process. And with B, linear graph between peak oxidation current and reduction current against the square root of the scan rate. The R square value 0.98 and 0 until 0.99. This one and this one. Indicating a strong linear relationship diffusion and control process. And with C, CV after modification with AU and PO or gold nanoparticles shows a significant increase in peak current. So indicating higher electrocatalytic activity and increased conductivity. And with D, the linear plot after AU and P modification also maintains that R square 0.99 remains diffusion controlled, but with a larger current response, confirming increased electron transfer efficiency. And the meaning of the figure 4 is the scan rate affects the current height, indicating a reaction mechanism that depends on analyte diffusion. The addition of OMP increases the conductivity and accelerates electron transfer. OMP modified sensors exhibit stronger redox response and higher sensitivity. This is about the figure 5, OMPLS sensor performance study. We go from 5A, differential pulse voltammetry or DPV graph of OMP modified PLSG electrode at various uric acid concentration from 10 until 750 micromolar. An increase in peak current is observed as the UA concentration increases. The peak occurs at around 0.2 volt, indicating the oxidation reaction of UA on the electrode surface. So the linear graph between peak current versus UA concentration shows a strong linear relationship. The R square is 0.984, indicating the sensor ability to detect UA quantitatively and accurately. And we see the reproducibility graph of three devices. Device 1 until 3 shows consistent current results for 100 micromolar UA, indicating stable sensor performance between devices. And with D, the time-dependent response graph shows that the current response remains stable up to day 18, indicating good sensor durability and storage stability. And the meaning of figure 5 is the ONP LSG sensor is capable of detecting uric acid in a wide range, 10 until 750 micromolar, with high linearity. It demonstrates good reproducibility and long-term stability. This performance confirms the potential of non-invasive biosensors for real-time monitoring of uric acid levels. And we got the table. This is about performance characteristics of LSG electrodes used in uric acid detection biosensors. Table 1 is about comparison of diffusion coefficients of different LSG electrodes with the redox mediator. This is kalium ferrocyanide and kalium ferricyanide. The diffusion coefficient value indicates how quickly redox molecules move around the electrode. The greater the diffusion value, the more efficient the mass transfer and electrochemical reaction. Therefore, ONP modified PLSG has the best performance because ONP increases the conductivity and active surface area of the electrode. The table 2 shows us about the determination of uric acid concentration in sweat samples by paper interface LSG, OMP modified PLSG biosensors. This table shows the results of uric acid level measurements in sweat samples using the OMP PLSG biosensor compared to standard sample or test solutions. Similar current values between standard samples and sweat samples indicate high accuracy. A recovery percentage between 103 until 108% means that the biosensor is capable of detecting uric acid with excellent precision and reliability in real environments or biological samples. And this is the table 3, advantage of the developed sensor compared to previous sensors. General table structure. The table compares 14 types of electrodes based on first detection method, electrochemical technique used such as DPV or amperometry or colorimetry and etc. And then the linear range or micromolar range of uric acid concentration that can be accurately detected. And then the response time required for the sensor to provide a stable signal, the LOD or limit of detection, minimum detection limit. The smaller is the more sensitive. Validation or real sample. Type of biological sample tested, such as sweat or serum or urine or plasma. And the last one is our reference from previous research. Sorry. The sensor can quickly detect uric acid levels within 1 minute, has a wide detection range and high sensitivity, low LOD. This is just 1.4. Its advantage is that it can be used directly on sweat samples, making it suitable for non-invasive detection without blood. This work is number one. So, comparison with other sensors. The example is in the Raut 2. This LSG on paper narrower detection range is 10 until 250, but the OLOD is higher. This is 3.97. The meaning less sensitive than the modified ONP version. And then one again, the example for example, MWCNT COHCE. This is fast response, 1 minute, but the LOD also high. This is 3.58 micromolar. And then this is the good one in this one. Compared to the previous sensors, this one is good. And this is the summary of table 3, advantages of the developed sensor compared to previous sensors. The table shows a comparison of various uric acid-based sensors, where ONPPLSG has a wide detection range, 10 until 750 micromolar, fast response time, 60 seconds, and low LOD, 1.4 micromolar, as well as validation on sweat samples showing the best performance compared to other sensors. It can be used directly on sweat, making it practical for real-time monitoring without blood sampling. Key innovation: the integration of laser-scribed graphene plus ONP improves electron transfer and speeds up sensor response. Okay, here's the critical analysis. Advantage method. First is non-enzymatic and non-invasive. Doesn't require uric acid enzyme and doesn't need blood samples. Secondly is direct printing technology. In this case, we use laser scribe graphene or LSG, inexpensive, fast, and without ink or additional chemicals. Small sample volume. We just use 20 microliters suitable for human sweat analysis. Modified gold nanoparticles. Because of this, enhances sensitivity and selectivity toward uric acid. Fast and accurate result. The response time is about 60 seconds with a limit of detection or LOD is 1.4 micromolar and high stability, 90% performance maintained up to 18 days of storage, and potential for wearable sensors, flexible and compatible with portable detection system. And then this is and then next about the limitations method. Still in the laboratory stage or prototype, not yet tested on a population of patients with varying clinical conditions, such as those sufferers. Limited sweat quantity. Difficult to apply if the user doesn't sweat much. And the third, other biological interferences, such as urea, glucose, or lactate, haven't been fully evaluated under actual bodily conditions. The fourth, no automatic sweat collection system still requires manual dripping on paper. So the last one is long-term testing. Durability above 1 month hasn't been conducted. Clinical potential. This biosensor has the potential to be used as a non-invasive tool for monitoring uric acid levels through sweat, which can be integrated into wearable devices for real-time detection outside the laboratory. This technology promises a fast, inexpensive, and user-friendly solution for the diagnosis and monitoring of metabolic diseases, although it still requires further clinical trials for validation in various patient conditions. And next, this is the clinical application potential. First is implementation in hospitals or clinical laboratories. This biosensor can be used directly near patients without large laboratory equipment, or we call it by POCT, point of care testing, and the device is portable and economical, suitable for clinical or field use. Uric acid is an important clinical biomarker for various diseases, especially thus related to purine metabolism disorders and inflammations. Uric acid levels can be monitored without drawing blood, making it more convenient and practical for clinical and home use. This biosensor is specifically designed for patients because it's non-invasive, real-time, and portable, making it a potential solution for continuous health monitoring. Future development direction, integration into wearable systems, and direct use in clinics or homes, as well as broader clinical validation. Okay, here's the last page in this presentation is conclusion. This study developed a non-invasive LSG RNP paper-based biosensor to detect uric acid or UA through sweat as an alternative to blood-based methods. The resulting sensor is inexpensive, flexible, sensitive, and accurate, with results comparable to standard laboratory methods. We use UHPLC-MS. This technology shows great potential for real-time monitoring of metabolic diseases such as gut, as well as development towards wearable clinical biosensors. Okay, the take-home message. This study shows that uric acid levels can be detected quickly, accurately, and non-invasively through sweat using an LSG RNP paper-based biosensor. This technology has the potential to become a real-time health monitoring tool for metabolic diseases such as gut, replacing conventional enzymatic methods that are expensive and unstable. With further development toward wearable and point-of-care testing or POCT, this biosensor could be a significant step toward self-diagnosis and personalized health monitoring. Okay, thank you. Maybe just this from me. Thus, I say wassalamualaikum warahmatullahi wabarakatuh.